So today we are going to look at a really cool geometric data structure known as the Voronoi diagram. It's going to take me a while to explain what it is, and then once we see how awesome it is, I'll show you how we can construct it, which is also pretty awesome. So the Voronoi diagram is a tool for answering near neighbor questions. So the idea is, if you're given a set of points, pi in the plane, and you want to answer queries for a given point q, and you want to find the nearest point. Okay, so near neighbor searching has a ton of uses. Finding the nearest post office, finding the nearest supermarket, finding the nearest document in various embedding spaces. So near neighbor search is a sort of fundamental problem, and we're looking at the geometric version when you have a set of points in the plane. Okay, so just to introduce immediately some terminology, I'm going to define V of pi to be the set of points in the plane that are closer to pi than to all other points. Okay. So let's try to understand the shape of these Voronoi. These are called Voronoi regions. Okay. And let's try to understand the shape of these Voronoi regions. So if I just have one point, then the Voronoi region is the entire plane, of course. Every point is closer to that than anything else because there isn't anything else. But suppose that I have 2 points. What are the Voronoi regions for these 2 points look like?
Half planes?
Yes. Which half planes?
Like you draw the perpendicular bisector of the segment?
Exactly. I take the perpendicular bisector of the segment connecting these 2 points, and that defines the boundary of their Voronoi regions, right? Now let's add a third point. And let me try and get it into general position. Here's a good place. Okay, I know that's still looking a little bit too isosceles. Hello. Let's go over here, say. Okay, so now that I have 3 points, how do I figure out the Voronoi regions?
You still like draw the perpendicular bisectors?
Yeah, I can do the same thing, right? For each pair of points, I can draw the perpendicular bisector. Okay. Now, we seem to have a problem because I've drawn these 3 perpendicular bisectors, and that creates 6 regions. But there's only actually 3 points. So how can I have 6 regions when there are 3 points?
Well, like 2 of the regions correspond to 1 of the points.
Yes, right. So if you think about it, what these 6 regions are identifying are not only the closest point, but also the second closest point, right? There's 6 of them because there are basically 3 factorial orderings of the points by how far away they are from a given query point. So we don't actually want all 6 of the regions if all we're interested in is the closest point, right? So in fact, Sorry, this is going to vanish the line. There we go. We get rid of some of these regions. Sorry, this is something that digital tools are not yet well set up for. So we have kind of half of each perpendicular bisector, right? And all right, so just filling in some words. If we have 2 points, then the shape of our Voronoi regions is defined by the perpendicular bisector. If we have 3 points, then we have 3 pairwise perpendicular bisectors. But what's interesting is that they meet at a so-called Voronoi point. Okay. Now you'll notice that I've drawn all 3 of them meeting at the same point. Is that some weird coincidence? I mean, obviously any 2 lines intersect, but why should all 3 of these lines intersect at the same point?
It's the circumcenter of the triangle.
Exactly. This is the circumcenter of the triangle. And in fact, it is equidistant from, by definition, from the 3 points. And that is why the 3 perpendicular bisectors all meet there. Yes? So let's see what happens when I add another point. Okay, I'll make some more perpendicular bisectors. And again, I'll have intersections. And you notice that adding a point actually sort of subtracted part of the previous Voronoi diagram, right? It's no longer relevant because it was separating 2 points, but now neither of those points is the nearest point because I've added another one. And just to sort of finish the story, I'll add another point over here, draw its perpendicular bisector. Okay, I'll also have a perpendicular bisector here. Right. So you can see that this is getting a bit complex. But what's interesting is that I'm now starting to create these closed regions. Sorry, fighting my eraser. Right? So as I add more and more points, I'm going to end up creating polygons that are the Voronoi regions of particular pairs of polygons. So people see how this is playing out as I construct this Voronoi diagram. So basically there are a bunch, it's sort of in the interior, you get these closed polygons. And what is that polygon? It's an intersection of half spaces, right? Which means that it's convex, right? And if you're on the inside, if there are points all around you, you'll get a closed polygon. If you're on the outside, then your polygon will open out to infinity in a direction where you are closer than everything else to the very remote points. Does this make sense in terms of the shape of the Voronoi diagram? Okay. So each Voronoi region is a convex polygon. Containing 1 point, right? And so that tells us that there are exactly n regions. regions, right? All of these regions are non-empty because a point is closest to itself. Oh, let me add though, I'm going to assume, let's see, do I need that yet? Yeah, I'm going to assume non-degeneracy. That there are no 4 points on a circle. And that's going to tell me that each Voronoi point is the intersection of exactly 3 of these perpendicular bisectors. Okay. Okay, so now we have this Voronoi diagram with these n regions. And now I claim that I've reduced the nearest neighbor problem to a problem that we already know how to solve, right? So the nearest neighbor problem is simply asking a question of which Voronoi region the query point is in, right? Now, how do I answer that question? Right, I've got this geometric arrangement that breaks the world up into polygons, and I have a query point, and I want to know which polygon it's in. Can I answer that question?
You like check each of the perpendicular bisectors and see which side it's on.
Ah, good. So I can certainly answer that question in order and time, right, in linear time. But that's going to be very costly if I have a large number of query points. Suppose that I wanted to pre-process the points pi to answer queries fast. Okay. Or at the moment, suppose that I was able to build this Voronoi diagram, right? And I'm going to put a star there because we don't know how to do it yet. But suppose that I was able to build the Voronoi diagram for these points. Can I now pre-process the Voronoi diagram in order to answer quickly the question of which polygon contains a query point? So this is a memory test, right? Who remembers what we learned in this class?
Maybe we can do persistent data structure and
yeah, this is in fact exactly what we saw in Slater, Tarjan, and Sarnak, right? We had a lecture on persistent data structures, which showed us how to build a point location, how to do point location, right? And the construction time was n log n. The space complexity was n, and the query time was log n. Okay. So that seems pretty good, right? We take this Voronoi diagram and we build a data structure that has that takes linear space. We can construct it in nearly linear time, and then we can answer queries about the containing polygon in log n time. And of course, those give us answers to the nearest neighbor query as well. Okay, so these two things fit together really, really nicely. Now there is a question that one of you should be asking me at this point. Okay, so when I talk about construction time n log n, space n, query time log n, what's n?
Number of Voronoi points?
Yeah. So the problem is that we, originally we're talking about query points, but this is in terms of the size of the Voronoi diagram. Right? And actually, I would say that the size is probably better captured by the number of segments of the Voronoi diagram as opposed to the number of points, since every point is in a segment, but you might worry that you have a small number of points and a large number of segments. Okay. So that points at something we have to answer, right? What is the size of a Voronoi diagram on endpoints? Okay. In order to answer that question about the point location data structure. Okay. So let me point out to you that the Voronoi diagram is what's known as a planar graph, right? Which is to say that the edges, the points are in the plane, and the edges don't cross. Right? Now, in a general planar graph, you can draw the edges curvy, right? So this is still a planar graph. In the Voronoi diagram, actually, by the way we constructed it, the edges are all straight. But that's just a special case of a planar graph. Okay. Now, I'm going to add a so-called point at infinity. To be the other end, the second endpoint of edges that keep going. Okay. Another way to think of this is that my plane where I'm doing the Voronoi diagram is actually on the surface of the Earth, right? And it curls around. So all of those points that seem to stretch out to infinity, they actually just reach around and meet somewhere in Australia. Okay, so my planar graph is on a sphere instead of being in the plane. And that makes it very clear that I can have a point at infinity. And now, in order to understand the size of the Voronoi diagram, we're going to invoke what's called Euler's formula, which says that in such a planar graph, the number of edges minus the number of vertices plus the number of faces is equal to 2. Here we have edges, here we have vertices, and here we have faces. Okay, we're going to use that in just a minute. Let's prove it by induction. Okay, so what we're going to do is we're going to consider our planar graph. Okay. Now, if let's see, how do I want to say this? If there's an edge with both ends having degree at least 3, I can remove it. Okay. Okay. I can remove such an edge. Now, when I do that, what does it do to the quantities n sub e, n sub v, and n sub f?
V and E both decrease by 1 and F doesn't change.
So if I'm removing an edge, then certainly N sub E decreases, right? Now, what did you say that V decreases? So V is the number of vertices. Okay, now you'll notice that I still have those vertices, right? So what changes?
F changes, not V.
Exactly. So the number of edges decreases by 1. Sorry, I wrote the formula wrong. My bad. It's N sub V minus N sub E. So here we have vertices. Here we have edges. All right, so the number of edges has decreased. The number of faces has also decreased. So the sum is unchanged. Yes? Now, another possibility, besides having all these degree 3 vertices, is if I have a degree 2 vertex. Okay. Now, with a degree 2 vertex that's connecting two edges, I can also remove it and just make one unbroken edge. Okay. What does that do to my counts?
Decreases V and E by 2, or by 1.
Number of vertices decreases by 1, and the number of edges decreases by 1. And so again, the sum is unchanged. Right? So I basically use the degree 2 vertex trick to get rid of any degree 2 vertex. Once I have only degree 3 vertices, I can apply the previous trick in order to get rid of any edge that connects a pair of degree 3 vertices, right? Eventually, you're going to take everything out and you'll just have a triangle left. Okay, and I can actually shortcut that triangle into a pair of edges that are connected, a pair of vertices that are connected by 2 parallel edges using the degree 2 vertex trick. And now it's just by inspection, right? I have 2 faces, I have 2 edges, and I have 2 vertices, so the sum works. So is everybody happy with this proof of Euler's formula? Now I'm going to use it to analyze the size of the Voronoi diagram.
Can I ask a question?
Yes.
Why do we end up with a triangle at the end?
Well, sorry, we will keep removing vertices until there are no vertices of degree 2. Sorry, we will keep going until there are no vertices of degree 3. Okay. Once there are no vertices of degree 3, once everything is degree 2,
we need an edge between 2 degree 3 edge, 2 degree 3 vertices to be able to remove
right. But again, as long as I have a degree 2 vertex, I can remove it.
No, but what if we have 2 degree 3 vertices that are not connected to each other?
Well, as long as I have any degree 2 vertices, I can remove them. So the only time I need to go back to the degree 3 case is when all of the vertices, is when no vertices are degree 2.
Okay, but I mean, what if we have like a number of degree 3 vertices that are not connected to each other so that we can apply this?
No, but that's the point. If there are no degree 2 vertices, then everything that's left, right? Notice that, sorry, I ignored here the fact that you can have a planar graph with actually, let's clean up the degree 1 vertices as well. They don't arise in the Voronoi diagram, but they certainly still apply with Euler's formula, right? So if we imagine having a degree 1 vertex, if I get rid of it, I'm removing 1 edge and 1 vertex, right? And not changing the number of faces. So I can get rid of degree 1 vertices and I can get rid of degree 2 vertices, right? And so all that's left at this point are vertices of degree at least 3. So now I can consider any edge. Its endpoints will have degree at least 3.
Okay, at least 3. It doesn't need to be exactly 3.
No, but that doesn't matter, right? The analysis works as long as the degree is at least 3.
Okay.
Okay.
Got it.
Okay, so now that we've got Euler's formula, let's think about how to use it to analyze the Voronoi diagram. Remember that we already said that the number of faces of our Voronoi diagram is just, there's 1 per point. So the number of faces is just n, right? Now, we also have that NV, well, that's by definition, is the number of Voronoi points. Right? And I argued before that each has degree exactly 3. Okay. Now we also know that each edge has 2 Voronoi endpoints. Right? So now I'm going to consider 2 ways of counting things. Okay. So if I take twice the number of edges, okay, this counts each end of each edge, right? In other words, it counts each attachment of an edge to a vertex. Yes? But I can count this a different way, right? If instead of going by edges, I look at each vertex and say, you have, so I guess another way to say this is that it's equal to the sum of the degrees of the Voronoi points, right? But we already know that every Voronoi point has degree 3. So here I write NV plus 1. Now why did I write plus 1? Because of the point at infinity. Okay. Actually, but the point at infinity may have a larger degree, so I actually need to put a greater than or equal to here. Right, you saw there were tons of lines heading off to infinity, so its degree is going to be larger. Okay. So I rewrite this now because Euler's formula gives me a relation between n sub e, n sub v, and n sub f. Okay. In particular, I know I can rewrite this as saying that twice n plus n sub v minus 2, or n sub f plus n sub v minus 2 is equal to 3 times nv plus 1, or sorry, greater than or equal to. But now we recall that n sub f is equal to n. Okay. And rearranging that tells us that n minus 2 is greater than or equal to nv plus 3 divided by 2, which means that nv is at most 2n minus 7. And so this is the crucial conclusion, right? That the number of Voronoi points is less than twice the number of input points. So our conclusion is that the number of Voronoi points and also the number of edges are both order of the number of input points. Everybody happy with that?
Can you go back to the top and explain what the persistent data structure is?
So that was lecture 2. Okay. So for those of you who joined the class late, you're going to have to back up and do a little bit of catch-up reading. So in lecture 2, we talked about persistent data structures and how they could be used to build a data structure for answering point location queries. In other words, which polygon contains a point. And although we didn't use the vocabulary at the time, it used the geometric notion of dimensionality reduction that I used in last lecture. Essentially, we said at any particular, on any particular vertical line, sorry, let me use a different color to make it clear what I'm doing. On any particular vertical line, okay, passes through a number of different regions that are linearly ordered. And their breakpoints are the line segments that define the boundaries of the polygons, right? So if I knew the order of these line segments, then I could find out which pair of them my query point was in between by doing a binary search, or searching a binary search tree on the vertical coordinates of, on the y coordinates of these line segments at the x coordinate of my query point. Is that clear?
Yeah, I was actually there for that lecture. I just forgot about this, but now I remember.
Forgetting, you should never, ever forget anything that was taught in this class. It is all just so important for your future life, right? But you see that this is applying that dimensionality reduction idea that we talked about last time?
Yeah.
Good. So we used the persistent data structure in order to be able to create all of the binary search trees that we needed by sweeping this red line from left to right and sort of incrementally updating the binary search tree as its topology changed when different lines intersected or split. Okay? And we showed that that could all be done in order n log n time and use only n space. And so that gives us our conclusion here, right? We know now that the Voronoi diagram has size order n, which means that we can build the point location structure in order n log n time. And it uses order n space. And that we can query it in order log n time, all of which are, you know, clearly just about as optimal as you can hope to get, right? Even one-dimensional queries, right? What's the one-dimensional version of this problem? Is I've got a set of points and I want to know which two I'm between. So for that, we need binary search. So even that is going to take log n time to query and linear time to build. So we basically get 2 dimensions for the price of 1, right? So great, we're done. We have solved the nearest neighbor problem, right? Anything we still have to do?
Construct the Voronoi diagram.
Exactly. One last detail, which is going to take the entire rest of the class, is constructing the Voronoi diagram. Okay. So this is actually another problem kind of like sorting. There are 17 different ways to construct the Voronoi diagram. Okay. And I'm going to show you one of them that will allow me to illustrate this idea of dimensionality reduction. But just for contrast, let me mention a one-sentence description of a Voronoi diagram algorithm. It turns out that the Voronoi diagram is the dual of the projection of the lower convex hull of the shape that you get by lifting all the points vertically onto a 3D paraboloid. So in other words, if we look at the reduced dimension version of this, if we wanted to solve the one-dimensional Voronoi diagram problem, we would draw a parabola and we would lift up every point to the parabola. We'd get points on the parabola. We would see which ones connect together in our three-dimensional shape. That would give us something that looks like, you know, a solid, a 3D geometric solid. And then we would project that solid back onto the plane, and the lines of that solid would be the Voronoi diagram lines. So that shows that you can solve the Voronoi diagram problem by solving convex hull in 3D. Which is not useful because I haven't shown you how to solve convex hull in 3D. So we're instead going to look at a sweep line algorithm for this problem. Okay, the basic idea is to sweep a line, and just to be consistent with all of the literature, I'm going to change directions. I'm going to sweep a line from top to bottom, and I'm going to build the Voronoi diagram at the sweep line. And so basically, as the sweep line descends, I'm going to sort of build out the shape of the Voronoi. It's going to be like a curtain dropping, right? That the Voronoi diagram is going to appear behind the sweep line. Okay. So we'll have this line, and behind the sweep line, we'll have this nice Voronoi diagram drawn, right? And as the sweep line descends, more and more of the Voronoi diagram will be revealed. Okay. Now there's a problem with this approach, which is we want the Voronoi diagram of the shape that is behind the sweep. We want the Voronoi diagram to appear behind the sweep line, but in fact, the Voronoi diagram is not fully determined by what we see above the sweep line. Why is that? Right, so if I tell you, okay, here are some points, right? And here is the perpendicular bisector, and here's the sweep line. So great, you know, I've only got 2 points. So I've got my Voronoi diagram, right? How could this be not the Voronoi diagram?
Like, I guess you could have some other point below the sweep line that determines.
Exactly. Imagine if there's a point that's right here, just below the sweep line, right? Then in fact, the Voronoi diagram involves that point, right? But if I'm only looking at the points behind the sweep line, right? So the problem is that a point below the sweep line can change the Voronoi diagram above the sweep line. Clear? So let me ask the next question. What points cannot change? What part of the area above the sweep line? Let me say it that way instead of what points. what part of the area above the sweep line is fully determined and not something that can be changed by any points below the sweep line?
I guess like anything that's that's closer to the highest point than the sweep line or something like that.
Exactly. Or I wouldn't say the highest point, but anything that is closer to an input point above the sweep line than it is to the sweep line itself. Why is that? Well, it's because the sweep line provides a lower bound on the distance to any point below the sweep line, right? So any point below the sweep line is not the nearest point. Is that clear? So let's think about this. What shape is that? So here I've got a collection of points that are above the sweep line. Here I've got the sweep line. What points are closer to one of the inputs above the sweep line than they are to the sweep line?
It's like
What is
the
that region?
point of the lower convex hull.
Well, so the lower convex hull, certainly, right? So I can draw this convex hull, and anything that's above this convex hull is certainly safe, right?
I mean, the midpoint of between the line and the lower convex hull.
Ah, okay. So you would want to look, I could take sort of midpoints below each, sorry, I should use some vocabulary. These points are called sites, just in order to distinguish them from all the other points in the plane. Okay, these are the sites that you want to get near. So yes, I could draw these sort of halfway points between the site and the sweep line, and I could connect them by lines, but I claim that that's still conservative. Okay, let's just consider a particular point. Can you tell me which points are closer to this point than they are to the sweep line?
It's a parabola.
Exactly, right? There's a parabola here of points that are closer to that site than they are to the sweep line. Similarly, there's a parabola here of points that are closer to this point than they are to the sweep line. And there's a parabola here. Right? And there's also a parabola here. Okay. So the safe region is this union of parabolas. Yes? All right. And sorry, I should say, we're talking about an algorithm that was, this is known as Fortune's algorithm. The guy is named Steve Fortune. It's not a way to get rich. Hard to get rich doing algorithms, although it can be done. So Fortune's algorithm, and so Steve Fortune named the boundary, these pieces of parabolas, are called the beach line. Okay. It's very poetic. You know, think about the water coming in on the beach. You've got these sort of separate flows that kind of all merge together into this kind of curvy shape. And so that's called the beach line. Okay. And Fortune's algorithm says that as the sweep line descends, we are going to trace out the Voronoi diagram behind the beach line. because that's where things happen and that's where we know things are stable, is behind the beach line. Clear? So the work of this algorithm is going to be to keep track of the beach line. Okay, so let's start thinking about that. And let's start by thinking about just one point and what we can say about what's going on. Okay, so we have this point which will be at a position x sub f and y sub f. It's the focus of the parabola. And we imagine our sweep line, which is at some point y equals t. Okay, and t is going to be decreasing over time. Okay, so the parabola equation is the one that satisfies, is the set of points that are equidistant from the focus, the site, and from the sweep line. In other words, x minus xf squared plus y minus yf squared, the squared distance from the point, is equal to y minus t squared, the distance from the line. Right? So all the points x, y that satisfy this equation are the parabola points. Okay. Now suppose that I fix x and I compute dy dt. And I want to find dy dt. Okay, so I'm going to differentiate both sides. And since x is fixed, the first term vanishes. And what I get is that 2 times y minus yf dy dt is equal to 2 times y minus t times dy dt minus 1, right? Differentiating by t. And if I rearrange that, I find out that dy dt is equal to y minus t divided by y sub f minus t. So this is the rate at which different points on the parabola descend as the sweep line descends. Make sense? And the thing that I want to take away from this is that if you have multiple parabolas, at a particular fixed x, then the lowest focus of those points, the lowest focus parabola descends the fastest. Right, because it will have the smallest value of y sub f minus t. And so it will have the largest derivative in magnitude. Okay. So that, now we're going to use that. Let's move on to considering, I have this one point, the sweep line descends, and I have this parabola, and at some point the sweep line reaches another point. Okay. Now, when we reach the second point, what happens to the beach line? Well, if you think about it, we basically start by creating a degenerate parabola at the moment that we hit the point, right? And then immediately that parabola begins to widen and descend as we move through the second point. Make sense? So we get a degenerate parabola, which a vertical line, which immediately widens to a regular parabola and joins the beach line. So now our beach line has two parabolas in it. Whoops, that's too terrible even for me. Here's one, here's another one. Okay, and you know, the one that we're closer to the beach line is going to be pointier, and because its focus is lower, it's actually going to descend faster as well. Okay. Now,
Excuse me. Can I
yes,
ask
go ahead.
why? So different points on a parabola descend with different speeds, right?
Correct.
On one parabola. So what do
Yes.
you mean by like the fastest descent parabola? Is the
So what I
lowest
mean
focus?
is, you see here that, let's look at this intersection of two parabolas, okay? These are interesting. So let me stack your question for a second. I'll get to the answer very quickly. So what is the intersection of two parabolas that appears in this beach line?
2
There
points.
must be something special about it.
Does it lie like in the segment joining the two foci?
Well, eventually it's going to fall below both foci, right?
Oh,
So
that's
it's
true.
not going to be on the segment joining both of them. But what mathematically, what can we say about this point? What mathematical constraints does it satisfy by being on both parabolas?
Well,
On the
they have its distance from the sweep line is the same for both, so its distance from the two foci must be the same.
Right. So because these 2 points, this intersection is at a particular distance from the sweep line. And since both parabolas are there, it's also at the same distance from both foci. So what are points that are at the same distance from two sites?
The perpendicular bisector.
Exactly. These are points that are on the perpendicular bisector. Right? In other words, as the parabolas descend, their intersection traces the perpendicular bisector. Right? So if I draw this perpendicular bisector, you can see that the two parabolas going down are their intersection point is actually going to travel on a straight line, which is the perpendicular bisector. Right? Now, let me flag something interesting about this. Notice that there's another intersection point. What's that intersection point doing?
It's like tracing the other way, right?
That's right. If you think about it, the other point is also on the perpendicular bisector, and that intersection point is actually going to rise, right? It's going to trace out the bisector in the other direction. Make sense? Now you notice this doesn't violate what we said, because this bisector in the other direction is still outside of the beach line. So we're going to be discovering things moving backwards, but they're still going to be outside of the beach line. Clear? So notice that even though we had two parabolas, the intersection of one with the other created three segments of the beach line, because one parabola actually ended up on two separate segments of the beach line. Clear?
I didn't get what you mean.
So what I said is that we looked at this intersection of two parabolas, and that defines the beach line, right? So the first part of the beach line is this piece of a parabola. It then intersects with another parabola, and the second part of the beach line comes from the second parabola. Okay. The third part of the beach line actually comes from the first parabola again. Right? So here's one segment, two segments, three segments of the beach line, each of which is defined by part of a parabola. But two of the segments are actually coming from the same parabola. Got it?
Yep.
Okay. So this moment when a sweep line hits a site, that is called a site event, because I guess Steve ran out of poetry naming the beach line. Okay. So again, if you think back to our persistent data structures, you know, there are these events that happen, these interesting moments where things change. And hitting a site is one moment where things change. Okay. Now, what other sorts of changes are going to happen? So, you know, above we have these, this bisector being traced out by our two parabolas, right? And let's just concentrate on one side of it. Okay. So as these parabolas descend, this bisector gets traced out. What other interesting events are going to happen?
Well, at some
What?
point your bisector might stop.
Good. So at some point, my bisector is going to stop. What does that mean it's going to stop? Well, if you think about the Voronoi diagram, what happens is that some other bisector hits it, right? And out comes a third bisector, right? So this is a Voronoi point, right? Now, what is happening on the beach line to cause this Voronoi point to occur? Okay.
Basically, like 3 parabolas hit at the same point.
Exactly. So what's happening at the on the beach line is that you've got a third parabola coming down. All right. And it is tracing out a perpendicular bisector with the second parabola. So let me get rid of this early part of the parabolas. Let's look when the sweep line is down here. Okay, so we've got two parabolas that are tracing out one bisector, and we have another two parabolas that are tracing out a different perpendicular bisector, right? And so we have two pairwise intersections of parabolas. But what happens is that at some magic moment, all three of those parabolas meet.
This algorithm is actually massive brain.
Is what?
Oh, sorry, I thought I was muted.
Go right ahead.
I was just saying this algorithm is insane. It
Yes.
just works. It just
Yes.
works like geometry.
Well,
I don't know.
It works because of geometry, right? So again,
Yeah, it's just crazy.
what is this? I should just retitle this course "Crazy Algorithms." I think people would enjoy that. Splay trees are just crazy, right?
Yeah.
Yeah.
And whatchamacallit? Maxwell is just crazy. It's just crazy algorithms. So what is special about this intersection of three parabolas? Okay, so three parabolas intersect when you are equidistant from three sites. which is exactly what we talked about, you're at a Voronoi point. The intersection of three perpendicular bisectors.
Why
Right?
should two of them be like tangent to each other necessarily?
I didn't say anything about tangent. I mean, it may look that way from my picture, right? But all I'm saying right now is that they intersect.
And that might happen like after some time that we cross the third point, not necessarily when we are passing, like when the sweep line is just passing the third point.
No, it will be, right. So at the moment the sweep line hits the third point, the parabola for that point will be degenerate. It'll just be a vertical line. So it can't really, I mean, that's an uninteresting moment, right? It's later after the sweep line is passed and we have a real parabola that it can sort of intersect with two other parabolas in order to identify a Voronoi point.
Right. And
Okay.
then at that point, the upper perpendicular bisector will stay fixed, and the bisector between like the third point and one of those 2 points will start growing, I guess.
Exactly. So what we see is, right, we had these three parabolas and there were two interesting pairwise intersections going on, right? So let me draw the more general, right? This is before, right? That we have these three parabolas and they're each tracing out a perpendicular bisector. And then later, these three parabolas have dropped, and now we get an intersection of all three of those perpendicular, of all three of those parabolas, which means that the two perpendicular bisectors are meeting. And then we proceed with two parabolas that define, right, the third pair now create the intersection that defines the third perpendicular bisector. Is that clear? Now let me ask, which parabola vanishes? Right, we have this intersection of three parabolas. And it appears that one of them vanishes, or actually, yeah. So which one is it? Well, it's the one with the highest focus because of our derivatives argument, right? Where we said that the higher the focus, the slower the parabola descends at a particular point, at a particular x coordinate, right? So the highest focus disappears and the two lower foci take over with a descent of their perpendicular bisector. Okay. Now this is called a circle event because we know that the Voronoi point is on a is the center of a circumcircle. Of a common circle containing the three of the three foci, or of the three sites. Okay, so the summary is that we have site events which add parabolas to the beach line. And we have circle events that remove parabolas from the beach line. Okay. Now, let me ask one question about this. Can a circle event add a parabola? I mean, again, maybe I have these three parabolas intersecting, and what's going to happen is that the third parabola was hidden and is now going to peek through and join the beach line. How do I know that a parabola is disappearing from the beach line instead of appearing on the beach line?
Wait, sorry, what do you mean by appearing?
Well, the question is, which thing, right, if this is the moment of intersection, what happens next, right? Which way is time going? Do I end up afterwards with this, or do I end up afterwards with this?
We should look at the focus points, I guess.
Yes, you can show that the answer is no, right? Because one of these because the middle parabola is vanishing. The middle parameter, the middle parabola will have the highest focus and vanishes because it falls behind. Okay. So now we've got our evolutionary model. Now we have to implement it, right? We have to implement something that tracks for the beach line. It needs to notify us of site events so that we can add a parabola, and also of circle events so that we can remove a parabola and mark a Voronoi point. And you know, I'm going to leave out some details here, but think about this, right? If we just imagine this simulation of the beach line, which every once in a while tells us, okay, you've got a site event here, and okay, you've got a circle event here. You know, when we see that circle event, we can say, okay, these are the three parabolas involved in the circle event. And so I can see what the perpendicular bisector is, or what the two perpendicular bisectors are. And so that tells me not just the Voronoi points, but also the Voronoi edges that connect those Voronoi points. Okay. So the way we do this is with a priority queue on the event times, right? A site event for a particular site, XF, YF, happens at time t equals y sub f, right? When the sweep line hits that focus. Okay. Now, how do we figure out circle events? And this really has shades of the persistent data structure. Okay. Circle events, they happen with a trio of adjacent parabola pieces. Right? So anytime we see three parabolas next to each other in our beach line, we can predict the time of the circle event. Right? Because we know we can compute the point that is equidistant from the three foci. And that gives us the coordinates of the circle event. And we can then figure out where the beach line is. Actually, the geometry of this is kind of pretty. If I make these three foci, then the, sorry, let me do it. That's going to be in the wrong direction. If I make these three foci, okay, the circle event is going to, sorry for the egg, but the circle event is going to happen when the sweep line reaches the bottom of the circumcircle. Okay, that's going to tell us where the circle event needs to happen. So we can put an event into the priority queue with the appropriate time for that circle event. Okay. Now notice that when a site or circle event happens, when it is pulled from the queue, and happens, well, that can change the sequence of parabola pieces. Right? Because after all, a site event will introduce a new piece of a parabola, and a circle event will remove a parabola or a piece of a parabola from the beach line, right? But we can find the location of the change by maintaining a binary search tree on the parabola pieces of the beach line.
You save them on an array, the parabolas and sequence?
Well, the problem with saving them in an array is that I want to be able to insert and remove, right? When I get a site event, that tells me I have to insert a parabola into the beach line. And so if I put them in an array, I would need to move over everything in the array to make room for the new piece.
Right. So we need like a tree or something.
Exactly. So we use a search tree. And when I have a query like, where should this new parabola be inserted? Well, I know the x coordinate of the new parabola. And so I use the binary search tree to find where in the order of parabola pieces this new piece should go, right? So in particular, on a site event, okay, we search in the parabola BST. And when we find the right location, we split the parabola that's there. And we add our new one. Okay, so this gets transformed into two pieces and a new parabola. Right, so we take one thing out of the binary search tree and we insert three things in the same location. Okay. Now you notice that this creates a new trio, or several new trios actually, right? There may be another parabola piece over here and another parabola piece over here. So what we have to say is, well, we just introduced a new parabola. So here are now three pieces that create a potential circle event. So I'll compute the coordinates of that potential circle event and I'll insert it into the priority queue. And similarly, I'll see on the other side that I've got three pieces that are a potential circle event. And of course, there's also a potential circle event with the parabola that I just inserted and the two pieces to its side. Okay, so I get these new adjacent trios of pieces, and I identify their future circle events, and I insert these into the priority queue. Right? Now you'll notice that it also eliminates certain trios. Right? You know, I used to have a trio of parabolas, but as soon as I insert one, now what was an adjacent trio is no longer an adjacent trio. Right? So I'm going to remove.
Trios?
Sorry, what was that?
What is trio, you mean? I don't.
So remember that a circle event happens, right? In order for a circle event to happen, you have to have three parabolas that are intersecting each other.
No, I mean the word trios, I guess.
Oh, a trio just means three things.
Oh, I see. And you just save like the intersection between like consecutive parabolas or just their focus points?
What you save is the time and location of the Voronoi point that they would create, the point that's equidistant from all three foci.
But I mean, in the tree that we want to like consider the trios.
Right.
Is
So
the trio
again,
consists of the focus points or the?
Right. So for the tree, what I preserve is simply a listing of the parabola identifiers. Right. This parabola, then this parabola, then this parabola.
And okay, I see.
Okay. But notice that some parabola identifiers may appear multiple times in the tree because a parabola can have several pieces on the beach line.
I see. So this thing that maintain their sequence is actually the pieces that happens by the intersection of parabolas.
Exactly. Exactly. Okay. So site event happens. We insert a parabola. This creates some new trios, and we have to put those circle events into the queue. It eliminates some old trios. So we will remove their circle events from the queue because they can't happen because those parabolas are no longer adjacent to each other, right? In much the same way, a circle event removes a parabola. And so that also creates and destroys trios. And so again, we insert or remove circle events. Okay, so that is the way that this event-driven simulation is executed, right? We look for the next change, and then we determine what the change is that we're inserting or removing a parabola piece. Then we update the relevant, we identify the trios that are created and destroyed, and we insert new circle events and remove irrelevant circle events as we do this. Okay. Now you'll notice that at any point, each parabola is only involved in a constant number of circle events with its neighbors, right? So the work of all of this is a constant number of heap updates or priority queue updates per site or circle event. Right? And also, besides the priority queue updates of inserting and removing new events, there's also just the delete min. But essentially, the number of operations is determined by the number of site and circle events. Now, how many site and circle events are there?
N?
Over the entire construction. So a site event occurs when you hit a site. How often does that happen?
N times.
N times. And when does a circle event happen?
When you hit a Voronoi point?
When you identify a Voronoi point. So how often does that happen?
Oftentimes.
Because we proved that there are order n Voronoi points. So there are n site events. There are order n circle events. And so overall, we're going to be spending order n log n time updating the queue.
And can
wait.
another proof for like the linearity of the number of Voronoi points be that like this in this procedure, every time we have a circle event,
Yes.
one
Yes,
parabola
you can actually prove it that way as well, right? If you want to have an algorithmic proof of the size of the Voronoi diagram, you can say, look, every time I have a circle event, I remove a parabola piece, right? Every time I have a site event, I only create two parabola pieces. So the number of removals is bounded by twice the number of creations and is therefore linear.
Got it, thanks.
Okay. So order n log n time updating the queue. So the summary is that we can build the Voronoi diagram in order n log n time. And once we have it, it will have order n space. We can then build the query structure in order n log n time. And it too will then have order n space. And after all of that, it will take us order n log n time to do our queries for nearest neighbor. So this is just beautiful, right? What started out as a very complex seeming problem turned into a problem of polygons and locating points. And by drawing together these algorithmic techniques of dimensionality reduction, sort of, breaking things down one dimension at a time and pulling in the whole persistent data structure concept, we were able to build a best possible, best imaginable data structure for doing nearest neighbor search. So any questions about that? I will mention one last thing. We talked about building this Voronoi diagram, right? Where you look at the bisectors of the points. And that gives you a certain shape. You can take all of these bisectors or all of these points and you can, sorry, I'm just making it big enough to show what I want to show. So here I have this Voronoi diagram. Imagine if I take the Voronoi diagram and I just draw a line between each pair of points. Okay. That is separated by a boundary. Okay. So if you think about it, this is actually going to create another graph, right? Which is called the dual of the Voronoi diagram. What you do is you draw an edge between any 2 points sharing a Voronoi boundary. And you can show that that this is a dual, that if you take the dual of the dual, you get the Voronoi diagram back. And what this means is, since the Voronoi diagram has points of degree 3, in the dual, all of the polygons will be triangles. All the faces of the dual will be triangles. And so what you've actually created is what's called a triangulation, where you're given a set of points and you're supposed to join them up into to make a network or to make a graph which is made up entirely of triangles. Okay, and triangulations are really, really important. You use triangulations when you're doing when you're solving partial differential equations for numerical approximation. You use triangulations when you're doing computer graphics and you want to represent a shape. You break it into triangles in order to render each triangle nicely and thus render the entire shape. So triangulations are really important in practice. And the triangulation that you get as the dual of the Voronoi diagram is known as the Delaunay triangulation. And in many ways, it is the best triangulation. And the reason is that it has no long, skinny triangles. Okay, so if you think about, doing some numerical approximation or something like that, if you have an incredibly long, skinny triangle, it means that the points are very separated from each other and your approximations tend to get bad. So instead you want to use fat triangles. And the Delaunay triangulation gives you the fattest possible triangles. So in fact, although the Voronoi diagram is cool, it's dual, the Delaunay triangulation is probably even more important in practice. But once you've constructed one, you get the other for free. So what I've shown you, an algorithm for constructing the Voronoi diagram, is also an optimal algorithm for constructing the Delaunay triangulation, which has tons and tons of applications. All right, so that's the end of what I have time to tell you about computational geometry. On Wednesday, we will begin our next topic, which I think will be online algorithms, although I might change my mind. I believe you're also in the midst of shuffling collaboration groups, because the next problem set will involve your next set of collaboration partners. Are there any final questions?
So this procedure was for 2D only, right?
Yes.
Algorithm.
Good. So the Voronoi diagram can be defined for any dimension. And it's a very interesting structure in higher dimensions as well. And building it is one of the core problems in higher dimensional computational geometry. And there are algorithms for it which have running times which are exponential in the dimension, which is typical for computational geometry.
But they're not, like, we had this, if I'm not mistaken, ND sort of runtime in persistent data structure, when we have the regions that we want to identify which one we are in. When we grew that dimension, it wouldn't become exponential.
That's right. But actually, for Voronoi diagrams, just the complexity of the shape itself is exponential.
And we have like a lower bound, which
yes, you can actually you can create sets of points where the complexity of the Voronoi diagram is quite high, is exponential in D.
And
I should double check that, but I'm pretty sure. Once you've constructed the Voronoi diagram, the point location data structure is, its complexity is not exponential in the size of the Voronoi diagram, but the Voronoi diagram itself is very large.
Right. And so like, do we also have a lower bound for like this general problem of finding nearest neighbor to be exponential in the dimension?
I'm not sure. I mean, the Voronoi diagram tells you that the complexity of the answer space is large, but it's conceivable that you could still find that nearest neighbor quickly using a different technique. I'm not sure. I'm sure the answer is discussed in computational geometry textbooks like Overmars, but I don't know.